Okay, so this video is going to talk about how the capacitance of a capacitor is determined. So here's the formula for the capacitance of a parallel plate capacitor, and we made sure to point out that the capacitance is determined by the physical properties of the capacitor only. In other words, just how it's constructed. So how good of a capacitor something is depends only on how it's made. And this formula just kind of appeared out of thin air to be used in the other videos. So here what I want to do is show you where that actually comes from, which is important because then if we have some capacitors that aren't parallel plates, then we can figure out what are the capacitance of those. There's many different ways to arrange these plates. They don't have to be parallel, and so we need to be able to figure out what's going on with those as well. So let me show you first where this comes from, and then that'll give us a recipe to find out where other capacitance come from. So just as a reminder, here's my parallel plate capacitor. The parameters of the physical construction that affect its capacitance are that each plate has an area A and they are separated distance D, and if you so that will determine the capacitance. And if you connect it with a battery, then this plate will get a plus charge and this plate will get a minus charge, and the electric field of course made between them is like this. Okay, so how do we find the capacitance? Well, the capacitance is defined as Q over V, and so if we can find the Q divided by the V, then we get the capacitance. And of course my goal is to show you that when you take this ratio you do indeed get something that is determined by the physical properties only. So first of all, as a reminder, when we say V, we mean the voltage difference across the two plates, and so we've been calling it voltage difference as just V for the entire circuits unit now. However, of course, back when we were doing exam 1 stuff, we used to call it just delta V. So we're kind of bridge the two worlds here. The kind of circuits stuff that we've been doing since homework 5, and we're actually going to go back to the earlier stuff where we're doing stuff in like homeworks 3 and 4. Actually, even going back to homework 2, so I guess I'll just say homeworks 1 through 4 stuff, where we used to call it delta V. So just remember we need to reconcile that a little bit. That's one of the reasons we wanted to keep homework, the newer stuff, separate from the older stuff, because that big notational change. So anyways, here we have it. Now we know that the electric field between the plates, that's sigma over epsilon naught. So that's a result that we've done several times now, so I won't recap why that is. And then if you wanted to get the voltage difference, of course, that goes right in here. We've been integrating to get the delta V. And so if we go ahead and put that in there, well, in this case, of course, the electric field, it happens to be constant, so we can pull that out. Integral of dr is just r, and in this case, the plate separation is d, so we get our delta V like this, and putting in our electric field, we get this. And again, this is actually trying to take care of whether it's a voltage gain or drop. If we're just looking for the magnitude, we're going to drop that minus sign there. So let's see what we get. C equals Q over, and then sigma D over epsilon naught. And now, of course, we need to reconcile the fact that the numerator is talking about Q and the denominator is talking about sigma. So remember that sigma is also Q over A. So let's go ahead and put that in there. Q D over A epsilon naught. We cancel the Q's, and presto, we have where that capacitance formula comes from for the parallel plate capacitor. Now it should strictly be said, of course, these are not infinite planes, so the electric field, you might question if we can use that, but this derivation, we sort of have our cake and eat it too. We take that the capacitor plates are finite, each of area A when we need to, but then we approximate that the electric field in between them is sort of close enough 2 if these planes were infinite, so we use that. So that's just for a lack of a better formula to use, because the electric field is going to be, of course, more complicated when these plates are not infinite. So we sort of use that formula because that's the best thing we have. So that's how that formula comes about, and we're going to take that and apply it to some other capacitors. So spherical and cylindrical capacitors. You can make capacitors in any sort of geometry. You just need 2 plates. Those plates just don't have to necessarily be 2 flat planes. So here's a spherical capacitor. Basically it's one metal plate that's like kind of a spherical shape. And then there's another one that's also of a spherical shape that is outside of it. So there's your 2 plates. If you got to connect the battery across them, so you have to kind of sneak one of the wires in, maybe through a hole here, and you connect it to the inner plate, and then we connect the outer plate, the outer spherical shell, to the other terminal, and we'll put plus charge and minus charge like that. So again, the prescription for finding the capacitance is C equals Q over V, and for V, remember this is really just the magnitude of delta V, and how you get that is you just integrate the electric field. And so if you know the electric field and you can integrate to get V, then you can do this. So I will remind you, the electric field between the plates, this is one of the applications you can do of Gauss's law. If you drop your Gaussian surface inside the inner plate or outside the outer plate, you will find the electric field is 0. Electric field is 0 here, it's 0 here. It's pretty much the same deal as out here. The electric field is 0 outside. So the only meaningful electric field is between the plates, and it looks like this. And as far as how you would do this, well, you could certainly drop a Gaussian surface in here and ask what's the electric field made, and of course, since this is a radially symmetric spherical charge distribution, the electric field is simply going to collapse to a point charge immediately, okay? And of course the Q enclosed here would just be plus Q. The minus Q is not inside the Gaussian surface, so it doesn't even count. Minus Q is not enclosed. Now you might wonder, why does it even matter if there's a second plate? If it's not enclosed, how is it going to enter the calculation? Well, I'll show you in just a second. Now, to get the voltage, you could certainly integrate here, but it would just be wasted work because, of course, you guys know what the voltage of a point charge is. So if the electric field collapses to that point charge, so will the voltage. And you can just start off there. And then remember that you're really looking for the voltage difference between the plates. And this is where the other plate will actually enter in. So you're trying to figure out the voltage difference between these two. So let's call it that the inner plate has a radius R1, and then the outer one has R2. So you're trying to figure out the difference between these two plates. That's V2 minus V1. So the formula will come out in terms of R1 and R2, or of course, if you want to make it as similar as possible to the other capacitor, the difference in these two radii is really the plate separation. So that's equivalent to the D that we're talking about here. So if you put that now, take the magnitude again, ignore all the signage, you just put it in here, and you take C equals Q over V, right? V really being the delta V. You put it in there. You will get something where everything cancels. Q is going to cancel. And you do get something which is only dependent on the physical properties of that thing, and that's the capacitance of a spherical cap. So I'm not going to spoil all your fun, but you will get something that again is dependent only on the physical construction and not on the particulars of what battery might connect to it or anything else. And that's one of the homework problems. Pretty much same deal on the cylindrical capacitor. Now we have a very, very long cylinder that goes on both directions, and another cylindrical plate that's concentric with it outside. And so again, if you wanted to hook this up to a battery, you'd need to sneak one wire here through some sort of hole, get it out inside there, connected to the inner cylindrical plate, and then the other wire would be on the outside. And so you could generate the plus charge on one and minus charge on the other. And same prescription, again, take C, Q over V, that is the voltage difference between the plates, and again, you need to integrate out from the electric field. So, the electric field, again, there's nothing on the very inside, no charge enclosed, no electric field on the outside, there's no charge enclosed, net overall. The electric field would only be in this region between these two, and your Gaussian surface you could throw right there. And the electric field, well, the plus charge would collapse immediately to a line charge, approximate as an infinite line charge. And you can of course look up what that is, but it's going to be lambda. It's going to depend on lambda, and it's going to of course be proportional to 1 over r. That's an old friend. And of course the minus charge is not enclosed at all, so we don't have to count that. The voltage, when you get that, that's of course integrating up. If this is going to go as 1 over r, then this voltage is going to be proportional to natural log something something. That's again an old friend. Remember that you're going to get the delta V first. The delta V will be the difference between these two, and so that's where the even though the minus charge isn't enclosed, that's how the radius of both plates is going to enter in. So if you want to call the radius of the inner one R1 and the radius of the outer one R2, you will get both R1 and R2 in this. And here, by the way, you don't have to do that pesky setting of an origin thing, because really all you need is delta V. So you can get this in terms of R1 and R2, and if you ever want to just talk about the separation of the two, you can of course call it D. And so once you get that, again, you just care about the magnitude, throw it into C equals Q over V. And when you are reconciling the fact that one is going to have Q and one is going to have a lambda, I will tell you that one of the things that will happen is you will have an L left over. Okay? So an L left over, it actually means that in this system, you will find that the capacitance is actually proportional to the length. So in other words, it depends on how long these cylinders are in order to say what the capacitance is. So we have a similar problem that we did in the parallel plate situation. We kind of have our cake and eat it too. We call them having finite area A plates each, but we use the electric field, of course, associated with if the planes are infinite, because that's the best we can do. It's kind of the same thing here. And so here, both of these plates do have a finite length L, but for lack of anything better to use, we do use the electric field associated with an infinite line charge, because that's the best we have. And so if you were to truly stretch these plates to infinitely long, you would have an infinite capacitance. So it's actually better here to talk about the capacitance per unit length of this kind of capacitor. And once again, you will see that it is only a property of the physical construction. There's no nothing left in there other than that. So again, I'll let you work that out on homework, and hopefully this gives you an idea. If you have any kind of weird geometrically oriented plates, you can make a capacitor out of them, and this would be your means to calculate what would be the capacitance of that. Now don't get me wrong, we most of the time work with parallel plate capacitors, but any plates arranged in some geometry have a capacitance. You can use two plates as capacitors. And it's, by the way, no accident that these three geometries, infinite plane, sphere, and cylindrical, these are the three geometries from Gauss's law, so those are the three most easily computed capacitances. So most of the time we'll use the parallel plate capacitors, but there are some homework problems where I ask you to go through this process, basically fill in the gaps of what I've just talked about here, to get your own capacitances for some other geometries.